Hello everyone, this is Dr. Young, and in this video, we're going to do the first part of our discussion of the reaction of alcohols and ethers with acids. And this will include a reaction called the dehydration of alcohols. I'm including it with all this other stuff, as you'll see, because it's mechanistically very related. And we'll just cover how alcohols react with acids in a variety of different conditions. So if you remember in the previous video, right, we've kind of talked about the reactivity of alcohols a little bit here. We've mentioned how they don't really do SN2 and E2 reactions very well. Right, and remember we said that in that part of that problem is that alcohols are really poor leaving groups. Right, because if that OH is going to get kicked off, it's going to become hydroxide. It's going to become OH minus, which is not very stable. Right, which is why it would burn you if you got it on you and mess up your eye forever if you got it in your eyes. It's not very stable, and it's actually a strong base, not a weak base. Remember, we want our leaving groups to be weak bases. So like this reaction here would just be nothing, right? Your fluoride is not going to kick out hydroxide. There's just no reaction there. And we also talked about how you want to be mindful of the fact that the OHs are weakly acidic. So if you add them to something like LDA, which is a strong base, the problem is that you're just going to do an acid-base reaction instead. So we said that there were other options, right? If, sorry, not that, there'd be no H there. This would just be O minus. Now, if I wanted to do an E2 reaction on that alcohol, on that hexanol there, the idea is that what I would do instead, right, if I really wanted to turn that alcohol into an alkene, one thing that I could do, and let me draw this so that it looks as similar to that molecule up there as I can get it. If I wanted to turn this into an alkene, all I need to do is use some other reagents I know. I can't do it directly with LDA, but I could get there. I could get there. Right, what I would do instead was I'd first turn that into a better leaving group, which we talked about in the previous video. So maybe something like SOCl2 and maybe TEA. All right, so that would turn this into a chloride. And then I could use my LDA, if I wanted, to then turn that alkyl chloride into the alkene, right? So there's ways around this, but I cannot directly take the alcohol to the alkene using a strong base. However, these reactions, these alcohols, are going to be reactive with acids, right? So they do react with acids. So alcohols and ethers can react with acids. Some at room temperature, some require higher temperatures. And so what I'm going to do to kind of help us organize these mechanisms, none of these mechanisms are going to be terribly new. They're going to look really similar to our SN1, SN2, E1, E2 stuff. But what I want to do is I want to organize this so that I'm talking about my hindered and unhindered alcohols and ethers, right? So if you take a look at my chart here, ROR for alcohols, sorry, ROH for alcohols, and ROR for ethers. And when I'm talking about the unhindered ones, I'm talking about the ones that are going to be easy to attack with the nucleophile, right? So I'm talking about methyl or primary, right? The small things, right? So a methyl alcohol or an ether with only primary groups on it. And when I'm talking about hindered alcohols or ethers, then I'm talking about secondary and tertiary, right? These are going to be the ones that can form carbocations more easily because, you know, tertiary carbocation, secondary carbocation, much more stable than primary methyls. And then up top here, I have my nucleophilic acids and my non-nucleophilic acids. And so I probably haven't really talked about those in quite those terms. So let me give you some examples of acids here. Let's say we have HCl, H2SO4, HNO3, HBr. I'll just do those four. These are all acids, but some of them are nucleophilic and some of them are non-nucleophilic. And I think it helps that if you take a look at what these turn into when they dissociate, right? So if you have H plus and you have Cl minus, or if you have H plus and you have HOS, double bond O, O minus, or in the case of nitric acid, right, that dissociates into H plus and then the nitrate. And then lastly, HBr, right, of course, will turn into H plus and Br minus. Now, by nucleophilic acids, what I'm talking about is acids that have conjugates that are good nucleophile. So these are things that have conjugates, right, the things they turn into. The conjugates are good nucleophiles. And again, if you remember back to our SN1, SN2, E1, E2 discussions, you should know what a good nucleophile is, right? We should recognize that Cl minus, we said that was a good nucleophile, right? It's small and it's got a full negative. Same thing with Br minus, that was small and had a good negative and had a full negative. So these nucleophilic acids are going to be things like HBr, HI, and HCl. In fact, those are really going to be the three because they're the strongest ones. HF is not quite strong enough for this stuff, but HBr, HI, HCl. And then that's going to mean our non-nucleophilic acids are going to be things like sulfuric acid or nitric acid. And these are non-nucleophilic, right? Remember, because the oxygens are so delocalized, the negatives on the oxygens are so delocalized that they're relatively stable. They're not high in energy. They're not really looking to do anything. You don't have localized electrons to go attack something and be a good Lewis base. So the non-nucleophilic acids are going to be the things that do not have very good nucleophiles as their conjugates. So things like H2SO4, we'll see phosphoric acid, H3PO4, nitric acid, perchloric acid in theory, stuff like that. Things that have conjugates that are not the halides. And so what we're going to do for the rest of this video is we're going to ask ourselves, what type of mechanism do you get if you combine an unhindered alcohol or ether with a nucleophilic acid? What do you get if you combine a hindered one with a nucleophilic acid? And we're going to fill in all four of these charts. So we're going to go over these examples right now and kind of figure out what type of mechanism. Do they go more SN1 or SN2 or E2, etc.? So let's look at our first example, right? And we just want to go through this like we would if we have no idea what the mechanism is, right? Ideally, you don't want to have to try to memorize very many mechanisms. You want to understand why they might happen. And so I'm going to split up my HBr. It's a strong acid, so I'm just going to make a note of that, right? So HBr is a strong acid. So I went ahead and I dissociated it, just like I would an ionic compound. So H plus, Br minus. And I'm going to go ahead and put on my partial charges. So I now have a partially negative oxygen and a partially positive hydrogen and carbon, right, from my polar bonds. So I want to ask myself, what's going to be attracted where? Now, I'm going to look at the bromine first, Br minus, and see if there's a good electrophile for it to attack, right? Is there something that's positive that has a good leaving group? So my Br minus would definitely be attracted to the H here, but the H doesn't really have a good leaving group on it, right? If you attack the H and the electrons went onto the O, you have an O minus, which is not very stable, right? And certainly not as stable as a Br minus. So that would be going uphill, not favorable. And that would just be acid-base reaction. It's not going to happen. Same thing if I have the bromine attack the partially positive carbon down here, right? We've said a few times at the beginning of this video and the last video, OH minus hydroxide is not a good leaving group, right? I'm not going to have my bromide attack from the backside or something and kick out the hydroxide. So I'm going to ignore the bromine for now. It looks like it's not really doing much at this point. The other thing I got going on is the H plus, right? And the H plus is going to be attracted to the partially negative oxygen. And so there's no real reason why you can't have, right, the electrons from your oxygen go and pick up the H plus. And in fact, that's what you're going to see for the first step in all of these reactions in this video. The first step is going to be that your alcohol goes and gets protonated by an acid, right? You're going to protonate your alcohol. Now, it's at this point that we need to ask ourselves, okay, I started off with OH, which we said was a poor nucleophile, or sorry, a poor leaving group. But now I have water. And water is a good leaving group. Right? Water is a good leaving group because if I have my oxygen take electrons back from the carbon right there, it's just going to become water. And we said good leaving groups are one, stable, water stable, and two, that they're weak bases, and water is a weak base. So I've suddenly turned my alcohol, which was a poor leaving group, and simply by protonating it, I've made it a good leaving group. And so now I want to ask myself is, well, will that water stay on or will it leave? And that's all about what type of carbocation is it going to leave behind. In this case, if water just left, I'd be left behind with a secondary carbocation. Right? And we know that secondary carbocations are relatively stable. Not as good as a tertiary. Relatively stable, sorry. Technical problems. Relatively stable. And so that's reasonable, right? If it was like a methyl carbocation, I wouldn't even propose this. If it was a primary carbocation, I wouldn't even propose this. Tertiary is great. Secondary is so-so. But we do have, and we should note, that we often heat these up. So you do have heat, so getting to a secondary is okay. Now, just like you saw with the reactions of SN1 substrates, or maybe you've done some additions to alkenes at some point, anytime you have a carbocation, you have to worry about rearrangement. It's not a property, it's not a characteristic of any one reaction type, it's a characteristic of carbocations. So if you have a carbocation intermediate, you have to wonder, is it going to rearrange, right? Because I do have hydrogens and alkyl groups on either side here, and it looks like, right, I could move to the right, but that's just going to give me another secondary carbocation. But if I move to the left, that's going to give me a tertiary carbocation. So what we see in this step is that the electrons, right, from the hydrogen, we have a hydride shift, are going to move over. We're going to have a hydride shift, so now that hydrogen that I drew in blue is over here now. And it's combined with, right, it's on the same carbon as the old H was there now. So I was able to go from a secondary to a tertiary. And then this may not happen in every example of this type of reaction, but you just want to be mindful of anytime you form a carbocation, can it rearrange? Will I have an alkyl shift? Will I have a hydride shift? Will a ring expand, etc.? And I'll try to show you some examples. So now I have a tertiary cation, which is more stable. And then I'm just kind of sitting here. But I'm going to sit here for only a short amount of time because, right, let's not forget about our bromide. Right? We said we had bromide, which is a good nucleophile. We've got a carbocation. And so if I just need to have my bromine attack my carbocation, and then I've got my product. And I've also, let's see, I also created water. Now, if I take a look at this mechanism, right, if I take a look at this, from here, from this point on, right, this kind of looks like an SN1 mechanism. I had a leaving group leave, and then I had the nucleophile add to that flat carbocation, right? In theory, you could have a mixture of enantiomers. In this case, there's no stereocenter, so I don't worry about it. But this is a very SN1-like mechanism. I had a nucleophile, and I had a highly substituted, I had a hindered substrate, right? We started off with a secondary substrate. And so every time you take a nucleophilic acid, right, which was this, anytime you take a nucleophilic acid and you react it with a secondary or tertiary substrate, you're going to go through this SN1 mechanism. You just protonate the alcohol, it's a good leaving group. The leaving group leaves, and then your nucleophile adds to that carbocation. So what we're going to do then is we're going to put that for this square right here, right? So we have our hindered alcohols or ethers. We just did an example with secondary. And we did our example with, I think, bromine, right, Br. So anytime we react a hindered alcohol or ether with a nucleophilic acid like HCl, HBr, or HI, it's going to go through an SN1 type of mechanism. It's going to be SN1-like. And everything you know about SN1 is still true, right? Tertiary is better than secondary. You may have rearrangements. You may get racemic mixtures of products. But what about these other combinations, right? What if I have a different combination? Here's a combination with hydrochloric acid, right? So we have another nucleophilic acid. We have another nucleophilic acid. And I'm going to do the same thing I did before. I'm going to draw out my H+, draw out my Cl-, put my partial charges on things. And like I was saying before, we're going to see the first step for all of these, right? The chloride can't kick anything out. We don't have any good leaving groups. But I can protonate my alcohol. So I'm going to have my alcohol get protonated by the acid. So if I protonate my alcohol, it's going to look like this. And then I want to ask myself again, okay, so now I've got the water, I've got the good leaving group. Is that leaving group just going to leave by itself, or does it need to get kicked off? And so if I want to know, like, well, is it going to leave by itself, right? I'll do an OR here. So we'll look at two possible mechanisms. So it's supposed to be just the same thing. I'm going to ask myself, well, can it just leave by itself to go this direction, right? Can it just leave behind a carbocation like before, right, and give me water? That's what we did in the last mechanism. And hopefully you're seeing what the problem is with this proposal, with this proposal for the next mechanistic step. The problem here, right, is that you have a primary carbocation, which is simply just too unstable. You're not just going to have your water just leave behind a primary carbocation. They're terrible, terrible intermediates, too high in energy. So in this case, the water is not going to leave by itself. It's going to just stay on here. And what's going to happen instead is that our chloride, right, we still have chloride around. Chloride could not attack this, right? The chloride could not come over here and attack the backside of this and kick out our hydroxyl because we said that was not a good leaving group. But now we do have a good leaving group. And so now our chloride can actually go ahead and do its backside attack and kick out the good leaving group, all in one step there. And hopefully you're recognizing from my language here, right? I just said that we're doing a backside attack, which should remind you of an SN2 type mechanism, because this is going to have an SN2 type mechanism. So this is all going to be SN2-like, right? We have a good leaving group. That leaving group is not just going to pop off. It's going to stay on there until a nucleophile attacks from behind. And so if you have and in this case, right, we have an unhindered substrate. We have an unhindered alcohol in this case, which means that that leaving group can't leave by itself because you can't form a good carbocation. So that nucleophile has to attack from the backside to kick it out. And so with this combination of reagents, so if I go back to this, right, we said this was SN1-like, but this is going to be SN2-like, right? If you have a unhindered alcohol or ether, I just did an example with a primary one, and a nucleophilic acid, you go E2. You go more of an E2 route. It's the kind of an E2 mechanism. Inversion of stereochemistry, all of that same sort of stuff is still true. Let's do another one, right? What if we have now a hindered substrate, and now we have for the first time a non-nucleophilic acid. I'm going to do the same thing. I'm going to break my acid up. So I've got H plus, H2PO4 minus. I've got partial charges here, negative on the O, positive on the H, positive on the carbon. And since I've said that this is a non-nucleophilic acid, right, I know that my H2PO4 minus is not going to be a nucleophile at all. It's not going to participate at all. It's non-nucleophilic. It's too stable. Those electrons are too delocalized. And I also said, right, that the first step for all of these is the same. You're always going to protonate your alcohol. And so I ask myself again, can this water leave, or is it stuck, right? Is the water stuck on there, or is it going to leave? It's going to stay on there if you have a methyl or primary. It's going to leave if you've got secondary or tertiary. And in this case, I've got a tertiary carbon, so my water can leave. Right, I've got a nice tertiary carbocation, very stable. And then I've made water, right? Water's come off. Now at this point, the water is a poor nucleophile. It could add back on, like, go SN1-like. But then that's why this can go backwards, right? Notice I made this reversible. It could just go backwards. And that's totally true. That could totally happen. But the other thing is just that I don't really have another nucleophile to add. So either we're just going to go backwards or something else has to happen. And remember when we said we had a carbocation and there's really nothing else going on and it was kind of boring and there was no like good reagent to make it do anything? That was our E1 reaction. And that's going to be the same thing for this. I've got beta hydrogens, right? I've got beta hydrogens here and here and here. And it's just like any other E1 where the idea is that you just go for the most stable alkene. You're going to go for the Zaitsev product. So what's going to happen is that one of the hydrogens here is going to fall off. It'll probably be picked off by water or something like that if you want to draw a base picking it off. But the idea is that it's going to fall off. It's going to be removed to give us an alkene. And again, this follows Zaitsev's rule. And we have H plus formed and water. And water form. And we've made an alkene. And I know I mentioned it before, but this should look a lot like an E1 mechanism. Leaving group leaves, you have a carbocation, a beta hydrogen falls off, gives you the Zaitsev product, and you form the most stable alkene that you can. And this reaction is called the dehydration of an alcohol. Has its own little special name, dehydration of an alcohol. And the idea is that you always form an alkene and you always have water as a side product, which is what we have here, right? We formed an alkene, we have water as a side product. That's what you're doing. So in a dehydration, let me write that out. You always have an alcohol plus acid turns into water and an alkene. And there are some sort of technical things that we don't necessarily have to go over with this, but the way you get this reaction to move forward is you have to get rid of the water. You need either something to absorb the water away or you need to boil off the water to get Le Chatelier's to help you out and keep moving forward to get the alkene. But either way, dehydration of alcohols, typically you're going to have a non-nucleophilic acid and your more hindered substrates. So let's add that, right? We said this was SN1, this was SN2, and we just did this, a hindered and a non-nucleophilic, and we said that that was an E1-like mechanism, and we call that a dehydration of an alcohol. Dehydration of an alcohol. So we just got one more combination, right? If you're probably following with me here. Now I need to see what's going to happen if I have a non-nucleophilic acid and I have an unhindered alcohol or ether. And this is the weirdest one, and I'm going to show it to you for the sake of its completeness, and then I'm going to totally bag on it and say never do it. So just follow with me here. So here would be an example, right? Again, unhindered substrate. Here I chose a non-nucleophilic acid. We'll come back to the fact that there's really high temperature, right? High temperature, high pressure. Talk about why we need such crazy amounts of energy for this. But I'm going to do the same thing that I've done for all these examples. H plus, HSO4 minus. I've got a partial negative, partial positive, partial positive. First step is the same first step. Go and get your hydrogen. Okay, so I've protonated my alcohol. I have that water on here. It's a good leaving group now. I ask myself the same question, can that water just leave by itself? And that answer has to do with, well, what type of carbocations is it going to leave behind? In this case, it would leave behind a primary carbocation, which is no good. Right, we're not going to leave behind primary carbocations. Too high in energy. And we don't really have a nucleophile to do a backside attack, right? Because we specifically chose a non-nucleophilic acid, right? If this was HBr, HCl, HI, just those halogens would attack from behind, kick out the water. But we don't really have that here. We have one of these conjugates. And so here's the step. I don't like it. I'm going to show it to you, but I don't like it. The reason why you need super high temperatures or pressures is that you need to get either this conjugate, this H2SO4, the HSO4 minus, or probably more likely, since it's probably a better base, to be honest, more starting material, you need to get one of those to act as a better base than it is and deprotonate a beta hydrogen. And so you're going to see water, or like I said, someone might draw a conjugate, pluck off that beta hydrogen, form the alkene between the alpha and beta, and kick out the leaving group. Right? And if you do that, you're going to form the alkene, and you're going to form more of your protonated alcohol, which then can react more and more and more and more. So your product would be this. And I'm kind of swallowing, I mean, this should seem kind of like, wait, what? You just said that alcohols are not the best bases, and you said that to do an E2 reaction, you need, right, this looks E2-like, it's all one step, it's concerted. You said to do an E2 reaction, you need a strong base, which I agree with. Yes, that's true. But that's kind of why, that's the rationale is why you need such high temperature and high pressure. Normally you do these in a bomb, which is just a sealed container. You heat them up above the boiling points of the individual molecules so that you can get this reaction to occur. And then if you do this reaction, like I said, you make a bomb, you put it behind a blast shield, and just kind of hope nothing explodes on you. This reaction is kind of ridiculous. Technically, people have done this, but you would never do this. I would never do this. If I wanted to turn this alcohol into this alkene, one too many carbons there, I would just try to do this a little more slickly and add just SOCl2 and like pyridine or something like that, right? Turn into the acyl chloride, and then just add, T-butoxide or something. Add a base. Not only would it be faster, but it'd be a lot safer. I could do it all at room temperature. I don't even really have to separate out. I don't have to purify really anything between the two of them. It'd be fine. It'd be much faster, much safer. This is a better route. As opposed to the top one. But it is a thing. You may see it in the textbook, so I feel compelled to show you. So that means, right, we started with the SN1, then we went to SN2, then we went to E1, and then lastly we have E2, but I'm saying really only with really high temperatures and high pressure. Right? You have to have a lot of pressure, a lot of energy in this. This is the worst one. That combination kind of is terrible. So that's kind of how we can look at how substituted is our alcohol or ether, and what type of acid are we reacting with it, so that I can get an idea of what type of reaction is going to occur. And I'll put right here now, and we'll talk about this in the next video, another example of a nucleophilic acid would be if you combined water and acid there, right? Because water is nucleophilic. It's a poor nucleophile, but it's nucleophilic. And so in the next video, in part 2 here, we're going to talk about, well, what happens if you add these things to alcohols and ethers. So we're going to do a lot of examples with alcohols first off, and then I'm going to show you what it's like for ethers and how ethers, it's the same thing. You just do everything twice, and then do some examples with ethers. So that's our plan. So study up, take good notes, and then watch part 2 of this video.